Good afternoon, everyone. My name is Amar. I'm a postdoc at the University of Groningen. And today I will be talking about the fabrication of flexible flow sensors made of PDMS and graphene using 3D printing and soft lithography. So let's first look at flow sensors found in nature, because nature has some of the best and very well optimized designs that we can of course take inspiration from. Here I am showing three animals: a fish, an insect, and a seal. And what connects the flow sensors found in all these three animals is the high aspect ratio of the flow receptors. We can see these magnified images showing that these are some very high aspect ratio structures. And the high aspect ratio results in a low bending stiffness in the flow receptors. And if you combine it with the high innervation that is found at the flow receptor base, the combination gives you a very high sensitivity of these flow sensors. So for example, you can see the numbers here that these sensors are really sensitive to very low flow rates. So the detection threshold is very low for these flow receptors. And that is mainly due to the fact that these are such soft and high aspect ratio structures. Now, if you look at the blind cave fish, just to delve more into an example, you can see on the left, if you follow my cursor, you will see a blind cave fish that is navigating through a Lego obstacle course. You can see that although it is blind, it is doing a very good job of navigating. And this is really because although it is blind, nature has endowed it with this so-called lateral line organ that is shown here. And if you look at the zoomed in view, you will see that this organ comprises of these tiny hair-like structures. Now, the sensing principle is very simple and yet very exquisite. When you get a flow disturbance, when you get a flow signal, the sensor bends. That fires neurons at the base, which lets the animal know of any impending danger around it. So this allows really the animal, using these arrays of the neuromast sensors, to form a 3D map of the flow field around it, even though it is blind. Now we take inspiration from this and make flexible high aspect ratio structures. And if we also pattern a strain gauge at the base, which typically has a high sensitivity, then we get both this combination of high bending strains due to the flexible cantilever and this high sensitivity, which mimics the high innervation density that I spoke about before. In the literature, people have used these cantilever flow sensors. So here I'm just showing three representative examples. Now, in these MEMS-based processes, people have used silicon as a substrate, and they use cumbersome processes such as CVD, electron beam evaporation, and backside etching to realize these cantilevers. But you can see that they are limited basically by the substrate, which is rigid, in this case, silicon. To overcome this problem, people have also tried to make these cantilever sensors using on flexible substrates such as Kapton polyamide. So Iyer et al., you can see, have made these cantilever flow sensors on a Kapton substrate, on a Kapton cantilever, which is also bent. And to realize this strain gauge, the piezoresistive strain gauge, they used carbon black. So another advantage of using flexible materials is that if you're outside the clean room, you can really be creative in your use of these piezoresistive sensing materials. Similarly, last year, Kaidarova et al. Patterned these laser-induced graphene strain gauges on, again, Kapton cantilevers. Then they use these flow sensors in some very nice applications to show how, if they put it on an animal, for example, how they can monitor the swimming speed of an animal, for instance. Now, just to summarize, the MEMS flow sensors were limited by the choice of a rigid substrate, which is silicon in this case, and the processes are cumbersome. So although they give very good resolution, people have also experimented with going out of the clean room and making flexible cantilevers. But these cantilevers that I've mentioned by Iyer et al. And Kaidarova et al., they suffered from a low gauge factor. Now, gauge factor is really an indicator of the sensitivity of a sensor, and I will talk more about this in the next slides. But the gauge factors were on the lower side. So to overcome this, we also want to make a high aspect ratio flexible cantilever flow sensor with higher sensitivity than that reported in the literature. So in our process, what we do is we first 3D print a mold with these micro protrusions, which are in a serpentine shape. Then we cast PDMS in the mold and we peel it off. So here you see a flexible PDMS cantilever with these microchannels. And then we drop cast conductive graphene ink solution into this. And we realized that the key to this process is this the micro dimensions of of these channels, because due to this capillary effect, the graphene readily flows through the cantilever through the microchannels, which gives us a very nice way of patterning these strain gauges. And after annealing and making electrical connections, we end up with a cantilever flow sensor, as you can see on the left. Now, our microchannels were about 150 microns by 150 microns, which is why we use this metal 3D printing process to give us such high resolution. And we are able to use piezoresistive graphene nanoplatelets ink as a sensitive sensing material for our sensors. Now, why do we use PDMS and graphene? Because this combination gives us high bending strains from PDMS and a high gauge factor from graphene. And to verify this, we did a test where we fabricated a PDMS tensile block with microchannel for the graphene nanoplatelets ink. After this, we subjected this block to strains in steps. So let's say 0, 0.3, 0.61, and so on. And then we loaded it to a strain of about 3.3% strain, and then we unloaded it in the same sequence. And we are constantly measuring the resistance of this cantilever as well, of this tensile block as well. And you can see that the gauge factor is defined as the fractional ratio of the ratio of the fractional change in resistance to the strain. We found it to be about 52 to 56, which is about 5 times more than that reported previously, for example, by Kaidarova et al. Last year. So this was a very encouraging result, which showed us that the graphene PDMS combination can give us very sensitive flow sensors. After that, we made our own wind tunnel in the lab because we were interested in the lower range of the wind speeds. So we made a wind tunnel with a test section of about 8 centimeters to 8 centimeters. We used the design guidelines available in the literature. This is a CPU fan, which if you supply different voltages to it, it can vary its speed. So it's a variable speed fan. And using this, we tested our sensors. Our sensor goes in through here in the test section, which is again 8 centimeters by 8 centimeters. So first, we tested the bidirectional sensing capability of the sensors. So we changed the direction of airflow impinging up on the cantilever. And we find that when the airflow impinges on the side of the strain gauge experiences a tensile stress, which means that a tensile strain, which means that the resistance goes up, which is positive. And if the airflow impinges from the other side, we get a negative resistance change, which means that the sensor is bidirectional. And we found that the sensor behaved much more stably in the compressive strain condition. So we performed our next tests only in the compressive state. To test this flow sensitivity, we again increased the flow speeds in steps. So we loaded the cantilever again up to a speed of about 10 meters per second. And then we unloaded it in again the same sequence. You can see that we do see some hysteresis here. So the sensor doesn't quite go all the way back to its original resistance due to the viscoelastic nature of PDMS. But in general, you can see that the hysteresis was minimal that we observed. We observed a high sensitivity of about 2.3 kilo ohms per meter per second, which was much higher than what was reported for similar cantilever flow sensors in the literature, which was again very encouraging for us, and which is really because of the high gauge factor that we noticed for graphene on PDMS. Similarly, we test the repeatability of these sensors. So in this case, what we are doing is we are switching the wind tunnel on and off for about 30 seconds. We do this for about 20 cycles. And you can see that the cantilever flow sensor behaves pretty repeatably. This represents an error of about 3% about its mean resistance change. So to summarize my talk, we came up with a facile and low-cost processing workflow. This entails 3D printing of the mold, peeling PDMS from these molds, and then graphene ink drop casting to realize a strain gauge at the bottom. These are high aspect ratio PDMS cantilevers, which give a high sensitivity due to the use of graphene nanoplatelets at the base. We measured a high gauge factor of about 52 to 56 to 3% strain. We measured good sensitivities to airflow of about 2.3 kilo ohms per meter per second. The sensor gave low hysteresis. It exhibited good repeatability and bidirectional sensing capability. In the future, what we want to do is really automate this process of graphene strain gauge patterning. Because for now, we are doing it manually using the capillary effect that I spoke about before. But it would be really good to do it to automate this process to improve sensor-to-sensor repeatability using inkjet printing. We want to test the sensor output in water, of course, against dynamic stimuli to really mimic the real world environment of fishes, for example. We want to fabricate arrays of these sensors, which is easy to do because this process is very facile. And finally, we want to employ these sensors on sensor arrays on robots for solve problems such as source seeking and so on. So with that, I thank you for your attention and I'll be glad to take any questions. Thanks again.